Check it out now, y'all.
nanoHUB-U, online instruction.
Hi, and welcome to Week 3, Lecture 2 of Dynamic Atomic Force Microscopy Methods. In this Week 3, we are focusing on online simulations using VEDA, which allows to do numerical experiments in a very realistic setting of dynamic atomic force microscopy. In the last lecture, we had shown you how to start running simulations for approach curves as you oscillate the tip and approach the sample. And in particular, we had talked about the fact that through a particular example, we had talked about how the simulation captures the attractive and repulsive regimes of oscillation and the transition that can occur between the two, and the coexistence of two oscillation states under certain conditions. And we had compared with prior literature that showed that the simulation is pretty well able to, or quite well able to, predict the existence of these two oscillation states and the point at which they jump from one to the other in comparison to the experimental results. What we wish to do today is we're going to continue with the approach curves example we started on last time and try to understand how does the choice of cantilever or the choice of operating conditions actually influence the transition between these attractive and repulsive regimes of oscillation. So the case one that we're going to study is going to be the dependence on free amplitude. The interaction parameters to be used for the simulation are briefly captured on this slide, but the appendix contains all the details. We have a 40 Newton per meter cantilever, and what we wish to do is, as we approach this soft sample, we wish to be able to understand how the choice of the oscillation amplitude far from the sample affects how does it influence the behavior of the microscope, whether it causes the microscope to operate more in the attractive regime or the repulsive regime, and so on. These things, by the way, may not be very intuitive when one first starts the atomic force microscope, and it's really when one does a lot of simulations that the broader picture of what combination of cantilevers and operating conditions is appropriate for your particular experiment really comes out. So the way one would proceed with this example is to go to the amplitude modulated approach curves tool, the basic tool, and you would load example 1. Remember, we already have these pre-populated examples out there. And what one would then do is simply change the very first entry in the operating conditions, which is the amplitude far from a sample, or the free amplitude, or the unconstrained amplitude. It is in the example, it's written as 30 nanometers, so you just have to change it to 20 and 10 and reduce it to understand what happens. And as soon as you change that one parameter, you just have to click on the very top bar on the simulate button on the very far right, and the simulation proceeds on nanohub.org. The results are going to be displayed in the form of the oscillation amplitude versus z distance. As you do these multiple simulations of different initial amplitudes, you can display all of them by selecting the bottom left. There's a little button that says All. So when you click on it, all the simulations are brought up. If you want to change the color of any one of those curves, you can go to the top right, and there's a little button in the blue colored button. If you click on it, it allows you to change the color coding for each of those curves that you're generating. What one notices in the amplitude versus distance graph is when you're far from a sample, of course, you have a constant amplitude, but then as one starts interacting with the sample, there's a reduction in amplitude, but then there's a sudden jump in amplitude, and the amplitude keeps going down. What's interesting is that the location where this transition from a slightly lower amplitude to slightly higher amplitude occurs, it really seems to depend a lot on the initial amplitude chosen. So, for example, in the smallest amplitude case, when we chose an initial amplitude of 10 nanometers, the amplitude just keeps decreasing without showing any of those jumps. So to really understand what is happening in these approach curves, it helps to look at the phase. And when one looks at the phase lag as a function of z, one notices that indeed what ends up happening is, in these cases, when you first approach the sample, the phase lag increases beyond 90 degrees, indicative of an attractive regime of oscillation. And then the transition to repulsive regime happens, where the tip is encountering a net repulsive gradient. And as you reduce the initial amplitude, or the amplitude far from the sample, we find that in the case, for example, when we had a far of 10 nanometers, we find that the phase remains always above 90 degrees, which suggests that as the amplitude is decreasing, we're staying for a longer part of the Z range in the attractive regime, and when the amplitude becomes 10 nanometers, the probe would continuously remain in the attractive regime of oscillation as the sample is approached. Another way to verify this is you could go to the results and choose to plot the average tip-sample interaction forces. We talked about the average tip-sample interaction forces a couple of lectures ago. And what one notices from this is that when the probe is in the attractive regime of oscillation, the average forces tend to be negative, attractive, and when we're in the repulsive regime, the average forces also tend to be positive. And in the case of choosing a small initial amplitude of 10 nanometers, we find that the average force is negative throughout the entire Z range, indicative again of the fact, or proving, in fact, that the tip stays in the attractive regime throughout. So the key advantage, if you were doing this experiment, is as you reduce the oscillation amplitude of the microscope, you actually tend to operate it in the attractive regime of operation without causing large damage to the sample. Case 2, we're going to look at the dependence of the attractive repulsive regimes on the cantilever stiffness. So we go back to the initial amplitude of 30 nanometers, load the same example, but now we're going to change the second property in the operating conditions table. It's originally at 40 Newton per meter, but we're going to change it down to about 20 Newton per meter and see what happens. In each case, when you change the value, just go up to the very top on the very right and click the Simulate button. So when you compare, for example, the 40 and 20 nanometer case, you see a very big difference in the amplitude versus Z curves. What one notices is that as the cantilever stiffness decreases, the cantilever tends to remain in the attractive regime for much longer. And in the case of 20 Newton per meter, what seems to happen is the cantilever remains in the attractive regime all the way down to the entire Z range over which the simulation is done. So by examining the phase, again, you can see that the smallest cantilever case, the phase lag remains positive throughout, and the average forces also actually remain positive, suggesting that softer cantilever would also lead to more chances for the microscope to be operating in the attractive regime of oscillation. Lastly, we're going to look at case 3, which is going to be the dependence on drive frequency. Now, the previous examples, we always had the drive frequency line up exactly with the resonance frequency of the cantilever, but in a lot of conditions and cases, one is interested in looking at drive frequencies a little to the left or a little to the right of the resonance frequencies. Again, VEDA allows you to do the simulations, and here we're going to do an example where we're going to compare it with prior published literature to see if we're able to capture the effects that have been seen in the literature. So this is an experiment performed on HOPG, highly oriented paralithic graphite, with a moderate or a soft to moderate stiffness cantilever with a large amplitude of oscillation. A far is 100 nanometers in this case. Again, all the interaction parameters and operating conditions for the simulation are listed in detail in the appendix. But the key thing I want to bring to your attention is the natural frequency is 52.4 kilohertz. The question we're going to ask is what happens to this transition between attractive and repulsive regimes when the drive frequency is exactly at natural frequency, and then when it's just a little below it, and when it's just a little above it. What we see on the next slide is an approach retraction curve where the amplitude is plotted as a function of z distance when the drive frequency equals 52.4 kilohertz. Now, what one finds in this case is the amplitude continuously decreases, and there are no jumps in amplitude that are observed. It turns out that if you look at the phase of this, that you will actually see that it tends to be in the attractive regime for the most part. And if you look on the right is the experimental result. That shows a very similar behavior, that there are no jumps in the amplitude as you approach the sample. In the next slide, we're looking at the case when the drive frequency is 52.6 kilohertz, just a little above the natural frequency of the oscillator. And when you look at the approach and retraction curves, there's a big difference now, in that when one is retracting, you have to go out a little further in Z before the amplitude comes back to the free amplitude that we saw earlier. So there's this interesting hysteresis that happens that is fairly typical of this coexistence of attractive and repulsive regimes of oscillation. And if you look on the right is the experimental result from the reference here that shows a very similar behavior. I just want to note that in the simulation on the left, the approach is the red curve, and it shows a bit of a spike at the point where Z is approximately 100 nanometers or so. That corresponds to an interesting transition that might have happened in the simulations, as one maybe intermittently jumped to a repulsive regime and then came back to the attractive regime, or vice versa. But on the whole, the trends and the points where the jumps occur are captured very well. In the last case, we're going to look at a case where the drive frequency is below natural frequency. And again, one finds that there is a hysteresis in the amplitude versus Z curves, whether you're approaching or retracting from the sample. A hysteresis that did not exist, by the way, when the drive frequency was chosen to be exactly equal to the natural frequency. And on the right is the experimental result that shows exactly the same kind of behavior. So, in conclusion, we have looked today using VEDA at how the choice of free amplitudes or amplitudes far from a sample, cantilever stiffness, and drive frequencies tend to influence this transition between attractive and repulsive regimes, which is so important to understand, to really understand or interpret data that you're getting from the microscope, and to optimize the conditions to probe the relevant properties of the material that you're interested in. Thank you very much.